There is a smell coming from a world 124 light-years away. You know this smell. It is the smell of the sea, that sharp, alive, faintly sulfurous exhale when the tide pulls back and the shore breathes out. On Earth, only one thing makes it: life. In April of 2025, the James Webb Space Telescope detected that molecule in the atmosphere of a distant planet. Two completely separate instruments, two separate wavelength ranges, the same result. The concentration was 10,000 times stronger than anything in Earth's oceans. The team spent months trying to make it disappear. They couldn't. No one has been able to explain it away. The data came from a world called K2-18b, a planet possibly covered horizon to horizon in a pressurized global ocean beneath a sky of hydrogen, locked to a dim red star, orbiting once every 33 days. Something in that ocean may be exhaling. Tonight, we trace the signal, meet the scientists on both sides of this extraordinary debate, and ask what the answer means, in either direction, for our place in the universe. If these films are worth your time, liking and subscribing keeps them coming. A world is out there. It has been breathing for 2 billion years without knowing we were listening. Now we are. The story begins not with a press conference or a headline, but with a scientist staring at a screen in Cambridge, England, watching a number that should have disappeared. His name is Nikku Madhusudhan. He runs the Atmospheric Research Group at Cambridge's Institute of Astronomy, and by April of 2025, he had been waiting for this particular number for the better part of 2 years. The first hint had come in 2023, when the James Webb Space Telescope turned its primary mirror toward a star 124 light-years away and read, encoded in the ancient light, a chemical fingerprint that should not have been there. His team spent the months that followed trying to make it go away. They tested every calibration assumption. They modeled every alternative molecule they could think of. They worked, methodically, and without any of the excitement that gets reported afterward, at the unglamorous task of proving themselves wrong. They could not. So they waited for a second observation window. This time using a completely different instrument, the telescope's mid-infrared detector, MIRI, operating across a wavelength range that has no overlap whatsoever with the first instrument. Different photon energies, different detector architecture, different calibration pipeline, different atmospheric chemistry window. If the signal in 2023 had been a ghost, a calibration artifact, a noise spike, a systematic error baked into the first instrument, this second instrument would not see it. Ghosts do not haunt two different rooms in two different ways at the same time. The signal appeared again. Think about what that means for a moment. Imagine you are trying to confirm whether a particular perfume is present in a sealed room. You bring in one expert, seal them inside, and they emerge saying, yes, it is there. You then seal that expert outside, bring in a second who uses an entirely different method, a chemical analyzer instead of a nose, sensitive to molecular masses rather than scent receptors, and they return the same answer. Neither expert has influenced the other. The methods share no common assumption. The results agree. That is the structure of what the James Webb Space Telescope produced at K2-18b. Two independent instruments, two separate wavelength ranges, the same molecule. Madhusudhan described the experience later in an interview. He said it was, in his own words, a shock to the system. He said it takes a while to recover from the enormity of it. These are careful words from a careful man. He is not given to drama. He spent his career building some of the most sophisticated atmospheric models in the field, and he had a precise understanding of what those words would mean the moment they were spoken in public. He used them anyway, because the data had done something to him that data rarely does to a working scientist. It had left him stunned. The molecule at the center of all of this is called dimethyl sulfide. You already know what it smells like, even if you have never heard its name. It is the smell of the ocean, not the saltwater freshness, not the seaweed exactly, but that particular sharp, alive, faintly sulfurous exhale that coats every shoreline in the world. when the tide pulls back and the algae bakes in the sun. That living smell. Every ocean on Earth produces it. Marine phytoplankton, microscopic photosynthetic organisms drifting in the sunlit upper layers of the sea, exhale it as a metabolic byproduct. Billions upon billions of them, every hour of every day, releasing this molecule into the air above every ocean this planet has ever carried. And in K2-18b's atmosphere, the James Webb Space Telescope detected it at concentrations roughly 10,000 times higher than anything found in Earth's oceans. Hold that number, 10,000 times. That is not a marginal enrichment, not a trace signal at the edge of detectability. That is a planet saturated with this molecule, the combined biological output of every ocean on Earth, multiplied, rising from a world we have never visited, orbiting a star we can barely see with the naked eye. Here is the tension that runs through everything that follows. The signal is real. The data exists. Two independent instruments on the most capable telescope our civilization has ever placed in space have both detected it, and months of active attempted disproof have not made it disappear. But science has a threshold for calling something a discovery, and that threshold has not yet been crossed. We are closer than we have ever been in the entire history of our species to finding chemical evidence of life beyond Earth. Closer is not there. And the question of whether we are looking at biology or at geology, at an ocean alive with organisms, or at a sea of molten rock producing the same smell through pure chemistry, is the question that is going to define the next decade of human astronomy. The planet this signal is coming from has no equivalent anywhere in our solar system. That fact matters more than it might initially seem. K2-18b sits 124 light-years from Earth in the direction of the constellation Leo. It has 8.5 times the mass of our planet and 2.5 times its radius. It orbits a red dwarf star once every 33 days, at a distance of roughly 13 million miles, less than a seventh of the gap between Earth and the Sun. It sits within the habitable zone of its star, the orbital band where liquid water could theoretically persist on a planetary surface. And it belongs to a class of world that planetary scientists have been trying to understand for 15 years without ever having been able to study one at close range. We call them sub-Neptunes. Too massive to be rocky planets like Earth or Mars, too small to be true gas giants like Jupiter or Saturn, with no analogue anywhere in our solar system and no nearby comparison case to send a probe to. And yet when the Kepler Space Telescope spent 9 years cataloguing planets across a wide region of sky, sub-Neptunes dominated the results so completely that they rewrote the field's assumptions about what the galaxy actually contains. Not Earth's, not Jupiter's. The most common type of planet in the Milky Way is one we do not have a single example of close enough to touch. K2-18b is our best current window into this dominant planetary class. Benjamin Fulton and his colleagues, working through the California Kepler survey in 2017, found something striking within the sub-Neptune population. The size distribution is not smooth. There is a pronounced gap, an absence of planets with radii between roughly 1.5 and 2 times Earth's, and planets cluster on either side of it like sand dunes parted by a wind. The explanation is photoevaporation. Smaller planets in close orbits tend to have their hydrogen atmospheres stripped away by stellar radiation over hundreds of millions of years, leaving behind bare rocky cores. The planets above the gap are those that held on. They retained something substantial against the stripping. K2-18b sits above the gap. It has held on to its atmosphere for over 2 billion years in the face of continuous radiation from a star close enough to bombard it daily. That is not a trivial thing. Retention on that timescale implies either a protective mechanism, a strong internal magnetic field perhaps, deflecting the charged particle stream, or an atmosphere so massive that even significant losses represent a small percentage of the total, or some combination of internal replenishment we have not yet fully characterized. Whatever the mechanism, the atmosphere is there. The question is what lies beneath it. The interior models offer 2 competing pictures, and both of them are physically serious. In the first, K2-18b has a rocky core under pressures that compress mineral structures into exotic forms that have no surface equivalent, a layer of high-pressure ice above that. Not ordinary ice, but water molecules locked into crystalline arrangements by millions of atmospheres. And above the ice, a global liquid ocean. No continents, no land anywhere. Water extending from one horizon to the other across an entire planet, pressing up against a thick hydrogen-helium atmosphere from below. On the ocean's surface, pressures roughly 10 times greater than at sea level on Earth. Temperatures elevated by the weight of that sky to levels that would boil any unprotected liquid on our world, but held in the liquid state by the pressure bearing down on it from above. This is what is called a Hycean world, and something in that ocean, according to the signal, may be alive. In the second picture, there is no ocean. Beneath the hydrogen sky lies a sea of molten rock at temperatures of thousands of degrees, churning with convection currents that cycle material across timescales of centuries. The chemistry between the magma and the overlying gas produces volatile compounds that drift upward. Methane, carbon dioxide, suppressed ammonia. From 124 light-years away, through the instruments available to us, the resulting atmospheric spectrum looks nearly identical to the first picture. Same molecules, similar proportions, same general fingerprint. No ocean, no life. The smell of the sea produced by heat and sulfur chemistry, nothing more. Both of these worlds are consistent with everything we currently know about K2-18b's mass, radius, and orbital parameters. The entire debate that has consumed planetary science for the past 2 years, the competing analyses, the statistical arguments, the methodological disputes, comes back to this single fork. Which surface is real? What is actually down there? To answer that, we need to understand how we read the sky of another world at all. We need to understand the instrument that found the signal, the technique that made it possible, and the extraordinary chain of physics that carries the chemical diary of an alien atmosphere across 124 light-years and deposits it, encoded and waiting, in the light arriving at our mirror. There is a magic trick at the heart of what Madhusudan's team actually did, and understanding it is essential to understanding why the debate that followed has been so fierce. The trick is called transmission spectroscopy, and to grasp it, you need to picture a very specific moment in K2-18b's orbit. Every 33 days, the planet swings around its star and passes directly between that star and us. From our perspective, it crosses the face of the star. This is called a transit, and it lasts only a matter of hours. During that window, something happens to the starlight that is almost impossible to fully appreciate. Most of the starlight is simply blocked. The planet's solid body stands in the way, and those photons never reach us. But at the very edge, at the thin ring where the planet's atmosphere meets the vacuum of space, some of the light passes through. It enters the atmosphere on one side, travels through hundreds of kilometers of alien gas, and exits on the other. And while it travels through that atmosphere, every molecule it encounters leaves a mark. Here is the key. Every molecule in existence absorbs light at specific wavelengths. Water absorbs at certain frequencies. Carbon dioxide absorbs at others. Methane has its own pattern. Dimethyl sulfide has its own pattern. Each molecule is, in effect, a filter, a barcode of dark lines stamped into the spectrum of any light that passes through it. When astronomers collect the starlight that has threaded through K2-18b's atmosphere and spread it into its component wavelengths, they can read those barcodes. They can see which frequencies were absorbed, which molecules did the absorbing, and in what quantities. From 124 light-years away, they can tell you what the air is made of on a world they will never visit. The light carrying that chemical diary left K2-18b over a century ago. It has been traveling through the void ever since, and when it arrives at the mirror, the information encoded in it is still intact, waiting to be read. This would have been impossible without the James Webb Space Telescope. Not extremely difficult. Impossible. The signal produced by molecules in K2-18b's atmosphere during a transit is unimaginably faint. The total dimming of the starlight when the planet crosses the star's face is roughly 1%. The additional dimming caused by the molecules in that atmospheric limb is a small fraction of that already tiny fraction. Detecting it requires a mirror large enough to collect enormous numbers of photons, instruments sensitive enough to separate wavelengths differing by fractions of a micron, and a position in space so thermally stable that vibrations and temperature fluctuations do not drown out the signal entirely. The James Webb Space Telescope has all of these things. Its primary mirror is 6.5 meters across, made of 18 hexagonal segments coated in gold, which unfurled in space like a flower opening in slow motion in the weeks after launch. It orbits at the second Lagrange point, a gravitational equilibrium 1 million miles from Earth, where it stays permanently in the shade of a sun shield the size of a tennis court, keeping its detectors cooled to within a few degrees of absolute zero. It is the most complex scientific instrument our civilization has ever placed beyond the atmosphere. And it was not designed for this. That last point matters. When JWST was conceived in the 1990s, the characterization of exoplanet atmospheres was not part of the brief. The telescope was built to see the first galaxies, to peer into stellar nurseries, to study the formation of solar systems in their earliest stages. Its capacity to read the chemistry of a planet's atmosphere emerged from the combination of its mirror size, its thermal stability, and its instrument precision, none of which were optimized for this job. This is worth holding on to when the data proves ambiguous. JWST is working at or near the edge of what its design allows when it reads the atmosphere of a world like K2-18b, which makes the two-instrument agreement all the more striking. NIR-SPEC, the near-infrared spectrograph, operates across wavelengths from roughly 0.8 to 5 microns, the near-infrared end of the spectrum, where carbon dioxide, methane, and the first hint of dimethyl sulfide left their marks in 2023. MIRI, the mid-infrared instrument, operates across a completely separate range, from 6 to 12 microns, a different region of the electromagnetic spectrum, sensitive to different molecular absorption features, produced by entirely different detector technology, with entirely different calibration assumptions. There is no overlap between these two instruments. There is no shared systematic error that could produce the same false signal in both. When they agree on a molecular detection, the agreement carries weight that a single instrument cannot provide. Before JWST, the planet's observational history was already teaching lessons about interpretation. In 2019, a team led by Bjorn Benneker detected what appeared to be water vapor in K2-18b's atmosphere using the Hubble Space Telescope. As modeling improved and JWST's more precise data arrived, it became clear that methane was a better fit to the absorption features Hubble had seen. The water signal was almost certainly a misidentification, not a failure of integrity, simply the natural process of earlier instruments being superseded by better ones. That history hangs over every claim made about K2-18b. The pipeline between a raw photon count and a final molecular spectrum involves dozens of decisions, calibration corrections, wavelength solutions, baseline subtraction, atmospheric retrieval modeling. At each stage, small choices can shift the apparent strength of a molecular detection. The same raw photons, processed differently, can yield different spectra. It is exactly why two independent instruments returning the same answer means something that one instrument alone can never establish. The framework that gives the detection its biological meaning was not built after the signal was found. It was built 4 years before it. In 2021, Madhusudan and a small group of collaborators sat down with a question that sounds simple but had never been properly asked. Sub-Neptune planets with hydrogen-rich atmospheres are the most common type of world in the galaxy. Had anyone seriously evaluated whether they could be habitable? The answer, when they worked through the physics, was yes. Under certain conditions, a sub-Neptune could maintain a global liquid water ocean beneath a thick hydrogen-helium atmosphere for billions of years. The hydrogen sky acts as a blanket, trapping heat through a pressure-induced greenhouse effect that keeps the surface warm even at orbital distances that would freeze a thinner world. Raymond Pierre Humbert and Eric Gaidos had already shown by 2011 that hydrogen atmospheres dramatically extend the range of conditions under which liquid water can persist. Madhusudan's team built on that foundation and asked what it meant for the most common planetary type Kepler had found. The answer produced a new class of world. They named it Hycean, a contraction of hydrogen and ocean. And what they found when they mapped out the conditions under which such worlds could exist was striking. The habitable zone for a Hycean planet is wider than for a rocky one. The thick atmosphere buffers against temperature extremes. The ocean could persist across enormous timescales, stable and deep and global, covering the entire planet from one side to the other, with no continents, no shallows, no land anywhere at all. Just water, pressing up against the weight of a hydrogen sky. The ocean surface on a world like this is nothing like any ocean on Earth. The weight of the atmosphere above creates surface pressures roughly 10 times greater than at sea level here, elevating the boiling point of water well above 100 degrees Celsius and holding the liquid in place against evaporation. The chemistry of the water at these pressures and temperatures falls outside any environment we have sampled directly. But liquid water, in whatever form it takes at those depths, remains the solvent in which chemistry can become biology. And then there is what a hydrogen atmosphere does specifically to the molecule at the center of this story. Dimethyl sulfide in Earth's oxygen-rich atmosphere is destroyed by ultraviolet light within days of being produced. The sun breaks it apart almost as fast as the phytoplankton can make it, which is why its atmospheric concentration stays low despite the enormous quantities continuously being released. In a hydrogen-dominated atmosphere, the physics is different. The overlying gas absorbs and scatters ultraviolet radiation before it reaches the lower layers. DMS survives far longer, 10 to 100 times longer than it would in our atmosphere. A modest biological source produces concentrations that would be unreachable on Earth. Small organisms in a Hycean ocean, exhaling this molecule into a hydrogen sky that barely touches it, could build up a signal that the most powerful telescope in history would detect from across the galaxy. From this, the 2021 paper derived a specific, falsifiable prediction. If biology exists in a Hycean ocean, dimethyl sulfide will accumulate in the overlying hydrogen atmosphere to concentrations detectable by the James Webb Space Telescope. That sentence was written down and published 4 years before the telescope confirmed the signal. Not a theory assembled to explain a result already in hand. A prediction made in advance, derived from first principles, committed to in writing, and then confirmed. There is one more aspect of the Hycean framework that cuts against the most intuitive objection. When most people hear hydrogen atmosphere and no oxygen, the instinctive reaction is that life would be impossible. Oxygen feels fundamental, but that feeling comes entirely from the specific history of life on this particular planet. Earth had virtually no free oxygen in its atmosphere for the first 2 billion years of life's existence. The organisms that thrived in that ancient world, the methanogens, the sulfate reducers, the iron oxidizing bacteria, did not merely tolerate an oxygen-free environment. Some of them are actively harmed by oxygen today. They are living reminders that the relationship between life and atmosphere is not fixed, but contingent, written by the conditions of the world where life happened to take hold. Sarah Seeger at the Massachusetts Institute of Technology took this reasoning into the laboratory. Her team placed cultures of Earth bacteria in pure hydrogen atmospheres and monitored what happened. The bacteria survived. They maintained metabolic activity. Life does not require what we assumed it requires. It requires only the conditions it evolved in, and those conditions can be radically different from our own. A world covered in a pressurized hydrogen ocean, lit by the dim red glow of an ancient star, may be stranger than anything in our solar system prepared us to imagine. But strange is not the same as uninhabitable. Strange, the Hycean hypothesis argues, might be exactly what life looks like on the galaxy's most common type of planet. That ancient red star deserves a closer look, because what it is and what it does to the world orbiting it shapes everything. The chemistry of the atmosphere, the physical structure of any ocean, the conditions any living thing would have to endure. And it introduces one of the strangest paradoxes in modern astronomy. K218 is what astronomers classify as an M2.5 dwarf. It has roughly a quarter of the Sun's mass and slightly more than a quarter of its radius. It burns so slowly, fusing hydrogen into helium at such a miserly rate that its projected lifespan runs to several trillion years, more than 200 times longer than our own Sun will last. By the time K218 finally exhausts its fuel and fades, the universe will be a place unrecognizable from the one we inhabit now. In stellar terms, at 2.5 billion years old, it is barely adolescent. Red dwarfs like K2-18 are not rare. They are the rule. Roughly 70 to 75% of all stars in the Milky Way are M-dwarfs, dim, cool, ancient, scattered in their hundreds of billions across every corner of the galaxy. The bright stars that define the constellations are the exceptions. The galaxy's true population burns too faintly to see without a telescope. If you picked a random star from the 400 billion in the Milky Way, your chances of landing on a red dwarf are better than 2 to 1. They are the dominant stellar type, and the sub-Neptunes that commonly orbit them are the dominant planetary type. The most common configuration of world in the galaxy is a sub-Neptune orbiting a red dwarf, and we have almost no idea what those worlds are actually like. K218b may be telling us. But K218 is not simply small and dim and long-lived. It has a character, and that character is violent in ways our own star is not. Young red dwarfs are some of the most energetically unstable objects in the galaxy. They erupt with stellar flares, sudden explosive releases of magnetic energy that dwarf anything our Sun produces. The largest solar flares in recorded history would register as modest events against the outbursts of an active M-dwarf. These flares release enormous pulses of X-rays and ultraviolet radiation, and they are accompanied by streams of charged particles that travel outward from the star at a significant fraction of the speed of light. For a planet orbiting close enough to sit in the habitable zone of one of these stars, orbiting, as K218b does, at roughly 13 million miles, less than a third of Mercury's distance from our own Sun, the radiation environment is nothing like what Earth experiences. Kevin France and his colleagues at the University of Colorado Boulder have spent years characterizing the ultraviolet environments of red dwarf stars and what they mean for close orbiting atmospheres. The picture is one of sustained bombardment, not just during flare events but continuously. The quiescent radiation level of an active M-dwarf is itself elevated compared to the Sun. Planets in the habitable zones of these stars receive UV doses that would sterilize Earth's surface many times over, and X-ray fluxes that drive photochemical reactions breaking apart molecules in the upper atmosphere at rates our planet never faces. K218 is roughly 2.5 billion years old. For a red dwarf, that is not old, but it is considered relatively calm for its type. Relatively, it still flares. It still batters its planets with radiation. The word calm in this context means that the frequency and intensity of its outbursts are lower than in the youngest and most violent M-dwarfs. It does not mean gentle. Here is where the paradox emerges. Everything just described sounds like a lethal environment for life, and yet red dwarfs are simultaneously the most productive hunting ground in the entire search for habitable worlds. The same orbital proximity that puts their planets in the radiation blast also puts those planets in transit far more frequently. K218b crosses the face of its star every 33 days. A planet in the habitable zone of a Sun-like star might transit once a year. More transits means more observations, more atmospheric data accumulated. The small stellar disk also helps. A transiting planet blocks a larger fraction of the light from a small red dwarf than it would from a vast, brilliant star. Red dwarfs are dangerous for life and ideal for finding it. And yet K218b has done something that demands attention. It has kept its atmosphere. For over 2 billion years, in the face of constant bombardment from a star that strips smaller worlds bare, it has retained a massive hydrogen-helium envelope. Whatever mechanism is responsible, a strong internal magnetic field generated by a hot, churning interior, or simply an atmospheric mass so enormous that even substantial losses represent a small fraction of the total, or some interior process continuously replenishing what the star strips away. The atmosphere is there. That survival is itself a piece of information. A world that has held on this long, in this environment, is a world that has something substantial to protect. Now consider what that star does to the planet's surface. K2-18b has been orbiting K2-18 for over 2 billion years at 13 million miles. At that distance, over that timescale, gravitational tidal forces have almost certainly done to K2-18b what they long ago did to the Moon in its relationship with Earth. They have locked it. Tidal locking is worth explaining carefully because its consequences for the planet are total. The Moon always shows us the same face. It rotates on its axis once every time it completes an orbit around Earth, keeping the same hemisphere pointed toward us permanently. This is not a coincidence. It is the end state of a process that begins whenever a large body orbits a smaller one, closely enough for tidal forces to be significant. Earth's gravity pulls slightly harder on the near side of the Moon than on the far side. Over millions of years, this unequal pull creates a gentle but continuous braking force on the Moon's rotation, slowing it until the rotation period matches the orbital period exactly. One face locked toward Earth, one face locked away, forever. The same process, operating over 2.5 billion years at K2-18b's orbital distance, would produce the same result. One hemisphere of K2-18b facing its star permanently. The same side, always, in perpetual day. The other hemisphere in perpetual night. The star fixed in the sky, never rising, never setting, simply hanging there above the dayside horizon for the entire history of the planet. Picture the dayside first. The star sits motionless, pouring energy continuously into the same hemisphere, heating the same atmosphere, driving the same chemistry without the daily cycle that governs everything about Earth's weather. Temperatures on the dayside could be extreme, not because K2-18 is especially luminous, but because there is no night to cool things down, no rotation to distribute the heat, no respite. The night side is the inverse. Permanent darkness, no direct starlight, ever. Temperatures plunging to perhaps 60 degrees below zero or colder, depending on how effectively the atmosphere circulates heat around the planet. Between them lies the terminator, a ring of perpetual twilight circling the entire planet, the boundary where day becomes night, where the star hangs permanently on the horizon, and long shadows fall across a world that never turns to face it and never turns away. This narrow band is the most thermally moderate region on K2-18b. Neither the blasting radiation of the dayside nor the deep freeze of the night reaches its full intensity here. If surface conditions anywhere on this planet are compatible with liquid water, with stable chemistry, with the persistence of complex molecules, the terminator is the most plausible location. The atmospheric circulation system driven by this configuration is unlike anything in our solar system. The temperature differential between the dayside and the night side is permanent and large. Hot air rises on the dayside, cools as it climbs, flows toward the night side at altitude, descends in the cold, and flows back along the surface. The result is a continuous wind system, hydrogen rushing from day to night, from heat toward cold, driven not by seasonal rhythms, but by the permanent geometry of a tidally locked world. Wind speeds along the terminator could reach hundreds of kilometers per hour, not gusts, not storms. A constant, planet-encircling flow of gas that has been moving in the same direction since the planet locked. If an ocean exists, it interacts with this system. Deep water has an enormous capacity to absorb heat, far more than any surface or atmosphere. And a global ocean on a tidally locked world would transport thermal energy from the perpetually heated dayside toward the perpetually cold night, buffering the temperature extremes at both hemispheres. The deep ocean layers, far below the surface, would barely feel the difference between the sunlit side and the dark one. Only the uppermost surface water would oscillate with any meaningful rhythm, and that rhythm itself is worth noting. K2-18b's orbit is not perfectly circular. It has a slight eccentricity, an oval path rather than a round one, that swings the planet a little closer to its star and then a little farther away across each 33-day year. The variation in received stellar energy across that cycle is roughly 43%. Every orbit, the energy input changes by nearly half. For microbial life in a surface ocean, this would be a pulse, a cycle of abundance and relative scarcity, of warmth and cooling, repeating with the rhythm of a world on a fast, tight orbit around a volatile star. Not a catastrophe, a season. And life, as the long history of this planet demonstrates, is extraordinarily good at adapting to seasons. All of that assumes there is an ocean. Not everyone at Cambridge believes there is, and the scientist making the most rigorous case against it works in the same building as the scientist who found the signal. His name is Oliver Shortall, and he approaches planets from the opposite direction to Madhusudan. Where Madhusudan's models begin with the atmosphere and work inward, Shortall's begin with the rocky interior and work outward. He is a geochemist by training. He thinks about planets not from the outside looking in, but from the deep interior upward, through layers of pressure and heat and chemical transformation the surface never reveals directly. And when he applied that approach to K2-18b, what he found was uncomfortable for the Hicean interpretation. At K2-18b's mass and density, serious planetary modeling suggests that what lies at the base of the hydrogen atmosphere is not water. It is rock, molten rock, a planet-wide sea of magma glowing at temperatures of several thousand degrees, churning with convection currents that cycle material from the deep interior and back across timescales of centuries. The idea is grounded in the same physics used to model rocky worlds across the solar system. Venus may have had a magma ocean in its early history. The young Earth certainly did. At K2-18b's mass, more than 8 times this planet's, internal pressures and temperatures during formation would have been dramatically higher. Shortall's models suggest a magma ocean may still be there today. Here is what makes this so consequential. A magma ocean in contact with an overlying atmosphere does not sit inert. Gases dissolve into molten rock from above. Others are released upward through volcanic outgassing from below. The magma acts as a vast chemical reactor, consuming some atmospheric constituents, generating others, reaching a steady-state composition that reflects the temperature and pressure at the surface and the elemental inventory of the planet's interior. This exchange has been operating, if the model is correct, for as long as the planet has existed. The atmospheric consequences are specific. K2-18b's atmosphere shows less ammonia than expected for a world of its bulk composition. Madhusudan's team pointed to this as evidence for biological activity, organisms consuming ammonia as a nitrogen source, stripping it from the atmosphere. It was one of the supporting pillars of the biosignature interpretation. Shortall's models offer a different explanation, requiring no biology at all. Magma dissolves nitrogen-bearing compounds readily at high temperatures. Ammonia in contact with molten silicate rock does not accumulate in the atmosphere. It dissolves into the melt. One observation, 2 completely different physical causes, no current way to distinguish between them from 124 light-years away. The situation with methane and carbon dioxide is the same. Volcanic outgassing from a hot silicate interior produces both gases in substantial quantities. Shortall's published models produce atmospheric compositions rich in methane, rich in carbon dioxide, and poor in ammonia, which is within the resolution of current observations, essentially identical to the atmospheric fingerprint of Madhusudan's Hicean Ocean. The same spectrum, the same molecules. One produced by a warm, pressurized ocean potentially alive with organisms. The other produced by molten rock with no life anywhere. From 124 light-years away, with current instruments, there is no way to tell them apart. And then there is the DMS signal itself. The conventional assumption is that dimethyl sulfide requires biology. On Earth, that is effectively true. The biological production rate dwarfs any known abiotic source, and the molecule has no significant geological pathway at surface temperatures. But K218b is not Earth, and its interior, if the magma ocean model is correct, operates at conditions far beyond anything accessible to Earth surface chemistry. At high temperatures, methane reacts with hydrogen sulfide, a volcanic gas released abundantly from molten silicate interiors, and can produce sulfur-bearing organic compounds, including dimethyl sulfide. The yields from this pathway, measured under Earth laboratory conditions, are lower than what would be needed to explain K218b's observed concentrations. But those measurements were made at room temperature and atmospheric pressure. The conditions at the base of K218b's atmosphere, temperatures of hundreds or thousands of degrees, pressures orders of magnitude beyond any standard laboratory, remain uncharacterized. The abiotic yield under those conditions is unknown. This is where Occam's razor enters the argument, and it cuts cleanly. A magma ocean world requires nothing extraordinary. No independent origin of life in a hydrogen ocean. No evolution of organisms capable of surviving pressures and radiation levels that have no analog in Earth's biology. No coincidence of conditions placing a productive biosphere at exactly the altitude and temperature required to release DMS into a hydrogen sky detectable by a space telescope. A magma world requires only that K218b behave as its mass, density, and orbital history most naturally suggest it should, as a hot, geologically active sub-Neptune, with a chemistry driven by the thermodynamics of molten rock meeting a hydrogen sky. Parsimony is not proof. The simpler explanation is not always the correct one, and the history of science is full of cases where the apparently straightforward interpretation turned out to be wrong, and the extraordinary one turned out to be right. But parsimony is where you start, and it is what you return to when two explanations fit the same data. Until new observations can separate the Hisian spectrum from the magma spectrum, until a measurement exists that one model predicts and the other does not, the geological explanation cannot be set aside. Both worlds are consistent with everything we know. The signal is the same. The surface could not be more different, and the question of which one is real has not yet been answered. There is a physical constraint on the Hisian interpretation that does not come from the spectrograph or the retrieval model. It comes from energy balance, from the simple, unavoidable arithmetic of how much heat a planet absorbs and how much it must reflect to keep its surface cool enough for liquid water to exist. The concept is called albedo, and it measures reflectivity on a scale from 0 to 1. A perfectly black surface absorbs every photon that strikes it, albedo 0. A perfect mirror reflects every photon back into space, albedo 1. Fresh snow sits close to 1. A dark ocean surface sits close to 0. Earth, averaging across its oceans and land and clouds and ice, reflects roughly 30% of the sunlight it receives, an albedo of approximately 0.3. Now here is the problem for K218b. The Hisian model requires a liquid ocean at the planet's surface, but the atmospheric pressure above that surface, generated by the weight of the enormous hydrogen-helium envelope, is roughly 10 times greater than at sea level on Earth. Under that pressure, water does not boil at 100 degrees Celsius. The boiling point rises substantially. The ocean can remain liquid at temperatures that would vaporize it instantly under ordinary conditions. This sounds helpful for habitability, and in some ways it is, but it comes at a cost. Higher pressure means the planet can absorb more heat before the surface boils, which means the planet can afford to absorb more heat than Earth does, which means, in turn, that it does not need to reflect as much of the stellar energy arriving from K218. That much is true, but the planet still receives a fixed quantity of radiation from its star, and independent calculations by two separate research groups, working from the known luminosity of K218, the measured orbital distance of K218b, and the surface pressure implied by its atmospheric mass, arrived at a number that stopped both teams in their tracks. For liquid water to exist at K2-18b's surface, given its atmospheric pressure and the stellar flux it receives, the planet would need an albedo of approximately 0.92. It would need to reflect 19 out of every 20 photons arriving from its star back into space. No known planetary surface achieves this. No ocean, no desert, no rocky landscape. The most reflective natural surfaces on Earth, freshly fallen snow, the brightest salt flats, approach albedos of around 0.9, and they do so only under ideal conditions, in specific locations, for limited periods. A global albedo of 0.92, sustained continuously across an entire planet, has no precedent in planetary science. The only mechanism that could plausibly produce it is cloud cover. Extremely dense, optically thick, high-altitude cloud layers blanketing virtually the entire planet continuously. Cloud decks reflective enough and persistent enough to bounce nearly all incoming starlight back before it reaches the surface. This is not physically impossible. Some models of thick hydrogen atmospheres do produce high cloud fractions under the right temperature and pressure conditions. But here, the second problem emerges. Cloud layers of the density and altitude required to achieve 0.92 albedo would leave a detectable signature in the spectrum. Dense, optically thick clouds at high altitude scatter and absorb light across a wide range of wavelengths. They would flatten and distort the molecular absorption features that JWST is reading. Their presence would show up, not necessarily as a cloud line, but as a systematic flattening of the atmospheric spectrum that retrieval models would identify. The current JWST observations of K2-18b show no evidence of this flattening. The spectral features are sharp and clear, more consistent with a largely cloud-free or thin cloud atmosphere than with the permanent thick cloud deck the albedo calculation demands. This is a genuine bind. Without the clouds, the surface is too hot for liquid water. With clouds of sufficient density, the spectrum should look different from what JWST is observing. The clouds are not detected. The Heisenkamp's response is technically correct, but epistemologically uncomfortable. Cloud modeling in exoplanet atmospheres is among the most difficult problems in the entire field. We cannot model the clouds of Earth with full accuracy, and Earth is a planet we can fly through, measure directly, sample at every altitude. Modeling the clouds of a world 124 light-years away from incomplete spectroscopic data involves uncertainties so large that the absence of a cloud detection cannot be treated as a confirmed absence. The absence of evidence is not evidence of absence. That principle is real and important, but it has limits. The albedo crisis does not disprove the Heysian hypothesis. What it does is identify the most physically demanding requirement that hypothesis makes, a requirement the current data does not support, and leave it sitting unresolved in the middle of the argument. The albedo crisis is a physical argument. The next challenge to the signal is a statistical one, and it cuts even closer to the center of the debate. When scientists describe the strength of a detection, they use a unit called sigma. It is a measure of how many standard deviations a signal sits above the background noise, a way of quantifying how unlikely it is that what you are seeing is a random fluctuation rather than a real phenomenon. The higher the sigma value, the more confident the detection. 3 sigma means the probability that the signal is simply noise, a random coincidence in the data, is approximately 3 in 1,000. In many areas of science, 3 sigma would be considered strong evidence. A 3 sigma finding in medicine, in ecology, in materials science would typically be publishable without question, and most working researchers would take it seriously. But physics, and particularly the subset of physics that deals with discoveries of fundamental importance, has adopted a different standard, 5 sigma. The probability of a noise artifact at 5 sigma falls below 1 in 3.5 million. This is not an arbitrary threshold. It is the level at which the scientific community has decided that the cost of a false positive, of claiming a discovery that turns out not to be real, is outweighed by the confidence in the result. 5 sigma is the threshold that was required to confirm the Higgs boson. It is the threshold used to confirm the first detection of gravitational waves. And it is the threshold that any claimed detection of a biosignature on another planet will need to meet before the scientific community accepts it as a discovery. The current DMS signal at K218b sits at approximately 3 sigma. The gap between 3 sigma and 5 sigma is not a bureaucratic formality. It is the difference between a compelling hint and an established fact, and crossing it requires more data, more transit observation windows, more photons collected, the statistical weight of additional measurements either reinforcing the signal or eroding it. Jake Taylor, an astrophysicist at Oxford, looked at the MIRI data with a method designed to remove a specific class of bias from atmospheric retrievals. Standard retrieval analyses begin by specifying a set of molecules to search for, then fit the data to models incorporating those molecules. This approach is powerful, but introduces a risk. If you are already looking for dimethyl sulfide, you may find traces of it in data where it is not actually present, because the model is specifically searching for its spectral fingerprint. Taylor's approach made no prior assumption about which molecules to search for. He fed the raw spectrum into an analysis that asked simply, what atmospheric composition best explains this data, without any prejudice about what that composition should contain? The answer his method returned was consistent with a flat line, no statistically significant molecular features. The spectrum, by this analysis, was not clearly distinguishable from noise. A team at the University of Chicago went further. They combined the 2023 NIRSpec dataset with the 2025 MIRI dataset in a single joint analysis, treating both observations together rather than sequentially. Their conclusion matched Taylor's. When both datasets were considered simultaneously, there was no statistically significant detection of dimethyl sulfide, nor of its structural analogue, dimethyl disulfide. Madhusudan's team responded. The critics, they argued, had used atmospheric models that were too simplified, models unable to reliably distinguish between molecules with overlapping spectral features at the resolution JWST provides. The Cambridge team expanded their own retrieval model to incorporate 650 molecules, a far broader chemical space than earlier analyses had considered, and found that dimethyl sulfide remained the most plausible explanation for the spectral features they were seeing. The critics pushed back in turn. The Cambridge model had changed substantially between analyses without any new observational data arriving to justify the change. Adding free parameters to a model, additional molecules, additional degrees of freedom, makes it more flexible, which means it can fit a wider range of possible spectra. A more flexible model is not necessarily a more accurate one. In the worst case, it is a model that has been tuned until it returns the result you were hoping to find, rather than the result the physics demands. Neither side has convinced the other. As of early 2026, the debate is ongoing in the published literature, with new analyses appearing, responses being filed, and the fundamental disagreement about what the spectrum actually shows remaining unresolved. The data exists. The photons have been collected. 2 sets of serious scientists, applying different but defensible methods to the same raw observations, are arriving at different conclusions about what those observations mean. This is science working exactly as it should, under the weight of the most important question it has ever been asked. The signal has not been confirmed. The signal has not been refuted. It sits at 3 sigma, contested, persistent, and waiting for more data that only the planet itself, crossing its star every 33 days, patient and indifferent, can provide. The field of astrobiology carries a particular kind of weight, not the weight of failure. Science does not fail when it corrects itself. The weight of memory, of having been here before, of knowing exactly what happens when an extraordinary claim travels faster than the evidence that supports it, and of the long, careful work required to rebuild credibility after the wreckage. On the 7th of August, 1996, President Bill Clinton walked to a podium in the Rose Garden at the White House and made an announcement to the world. A team of NASA scientists, he said, had found compelling evidence that might point to the possibility of ancient primitive life on Mars. He spoke carefully, but the sentence barely mattered. The word life and the word Mars in the same breath from the President of the United States. The interpretation was instantaneous. The world held its breath. The object at the center of the announcement was a piece of rock roughly the size of a potato. It was a fragment of Mars, blasted off the Martian surface by an ancient asteroid impact, drifted through space for millions of years, fallen through Earth's atmosphere, and been found in the blue ice of the Allan Hills region of Antarctica in 1984. It was catalogued as ALH 84001, and what David McKay's team at NASA's Johnson Space Center believed they saw inside it was remarkable. Microscopic structures resembling fossilized bacteria, polycyclic aromatic hydrocarbons produced when organic material breaks down, carbonate mineral globules associated with biological activity, and crystals of magnetite bearing a striking resemblance to those produced by certain bacteria on Earth. 4 lines of evidence. Taken together, the team argued, they were consistent with ancient Martian microbial life. The years that followed dismantled each one. The microscopic structures were far smaller than any known living cell, and experiments showed that nearly identical forms could be produced by inorganic chemistry with no biology. The polycyclic aromatic hydrocarbons were found throughout the meteorite, including in zones exposed to Antarctic contamination from Earth organisms. The carbonate globules were explicable by high-temperature chemical reactions. The magnetite crystals remain the one genuinely contested piece of evidence. Some researchers still argue they show biological characteristics, but stripped of the other 3 supporting pillars, they cannot carry the weight of a discovery alone. The case collapsed, not because the scientists were dishonest, not because the evidence had been fabricated, because the desire to confirm the discovery had moved faster than the evidence could support, and because science, when it functions correctly, does not allow that gap to persist indefinitely. What ALH 84001 left behind was not only a failed claim, it left protocols, tighter contamination detection standards, a field-wide understanding of how easily the desire to find life can color the interpretation of ambiguous data, a new vocabulary built around the need for biosignature ensembles, multiple converging lines of evidence rather than individual molecules, before the word discovery could be used. Then came 2020 and Venus. Jane Greaves at Cardiff University and her collaborators announced the detection of phosphine in the cloud deck of Venus. Phosphine is a molecule of 1 phosphorus atom and 3 hydrogen atoms, and on Earth, it is produced in 2 contexts: certain bacterial metabolisms in anaerobic environments and industrial chemistry. No known abiotic process in a planetary atmosphere produces it in significant quantities. If phosphine was genuinely present in Venus's clouds, something was making it. The media response was immediate and almost universal in treating the detection as near confirmation of life in the solar system. The reanalysis came quickly. Multiple independent groups found that the absorption feature identified as phosphine sits at a wavelength overlapping with sulfur dioxide. A gas Venus has in abundance. A calibration error in the original pipeline had amplified the signal. When corrected, the phosphine detection dropped from roughly 20 parts per billion to approximately 1, consistent with ordinary photochemistry and no biology. Geronimo Villanueva at NASA found no convincing evidence of phosphine in his own independent analysis. The discovery was retracted. What Venus phosphine left behind, like ALH 84001 before it, was not nothing. Better spectral analysis procedures, improved calibration standards, a sharper awareness of how overlapping molecular features can mislead even careful researchers at the edge of instrument sensitivity. Jake Taylor's unbiased retrieval approach, applied to K2-18b years later, is a methodological descendant of the lessons learned from Venus. The pattern is clear enough that some scientists have drawn it explicitly: the extraordinary spectral claim. The immediate media amplification translating qualified language into confirmed discovery. The swift community reanalysis. The contested or collapsed signal. The methodological advance that emerges from the controversy as a permanent contribution, regardless of the outcome. K2-18b is following this script with enough precision to make seasoned astrobiologists uncomfortable. But it is not following it completely, and the differences are real. The phosphine detection rested on a single instrument, a single observation run, a single spectral feature at a wavelength that directly overlapped with a mundane atmospheric constituent. The K2-18b signal has been returned by two independent instruments operating across completely non-overlapping wavelength ranges. There is no shared spectral overlap to invoke. There is no single calibration pipeline whose correction would dissolve the detection. The signal has survived months of active attempted disproof by the team that found it. And it was predicted by a theoretical framework 4 years before either instrument collected a single relevant photon. These differences do not establish that the signal is biological. They establish that the K2-18b case is structurally more robust than anything that preceded it, and that dismissing it as simply another Venus phosphine episode misrepresents the evidence. The signal has been contested. It has not collapsed. Those are different things. Here is the underlying problem with every biosignature claim ever made, including this one. Every molecule that life produces, chemistry can also produce. Every single one. Oxygen in a planet's atmosphere is the canonical example of a biosignature, the product of photosynthesis, the marker of a biosphere that has been splitting water molecules and releasing oxygen as waste for billions of years. And yet ultraviolet radiation can also split water molecules, releasing hydrogen into space and leaving oxygen behind. A water-rich planet close to an active star could accumulate substantial atmospheric oxygen without a single photosynthetic organism ever evolving. The oxygen would be there. The life would not. Multiple research groups have modeled this scenario in detail, and the result is clear. Oxygen alone cannot be trusted as a biosignature without understanding the full environmental context of the planet it is found on. Methane has the same problem. Volcanic outgassing produces it. Serpentinization, a reaction between seawater and certain deep-sea rocks, produces it. The atmospheric chemistry of gas giants produces it through purely physical processes. Finding methane in an exoplanet atmosphere tells you that carbon and hydrogen are present, and that conditions somewhere on or in the planet favor their combination. It does not tell you that anything alive is responsible. And dimethyl sulfide, despite its remarkable specificity as a biological product on Earth, has an abiotic escape route too. The Rosetta spacecraft, operated by ESA, spent 2 years studying the comet 67P Churyumov-Gerasimenko before landing on its surface in 2016. The Rosina instrument, the spacecraft's mass spectrometer, detected dimethyl sulfide in the volatile ice of the comet's nucleus, a 4.5 billion-year-old object assembled from the primordial debris of the early solar system, with no biology, no cells, no chemistry more complex than what physics and temperature and the UV environment of interstellar space could produce. And there, locked in ancient ice, was the molecule whose detection in K2-18b's atmosphere is being considered potential evidence of life. Dimethyl sulfide forms in space without life. That fact does not dissolve the K2-18b signal, but it means the signal cannot rest on the molecule alone. The field's answer to this problem took decades to develop, and it is still being refined. The core insight is that single molecules are inherently ambiguous. Every one of them has an abiotic escape route, but combinations of specific molecules may not be. The approach is called biosignature ensembles, and the logic is elegant. Oxygen and methane react with each other continuously in an atmosphere exposed to starlight, consuming each other on timescales of thousands of years. If an atmosphere contains both gases simultaneously at significant concentrations, something must be continuously producing both faster than the reactions destroy them. On Earth, photosynthesis produces oxygen and methanogenic bacteria produce methane, the biosphere maintains both against the thermodynamic pressure of the chemistry that would otherwise eliminate them. No purely geological process is known to replenish both gases simultaneously at the rates required. The oxygen-methane ensemble is therefore far more diagnostic than either molecule alone. K2-18b cannot use this test. In a hydrogen-dominated atmosphere, free oxygen reacts with the hydrogen almost immediately and disappears. The gold standard ensemble is chemically unavailable for this world, which is why methyl chloride has become the most important additional target in the current search at K2-18b. On Earth, methyl chloride is produced primarily by vegetation and marine organisms. No known abiotic process in a sub-Neptune environment generates it at atmospheric concentrations. Its spectral absorption features fall in a range accessible to JWST, and crucially, methyl chloride shares no known production mechanism with dimethyl sulfide. They are chemically unrelated, metabolically unrelated, and would require entirely different sources to explain. If methyl chloride were detected at K2-18b alongside the DMS signal, the two molecules together would constitute genuinely independent biological evidence, closing off the abiotic escape routes that either molecule leaves open on its own. Sarah Seeger at the Massachusetts Institute of Technology has been thinking about this problem longer than almost anyone in the field. In 2025, she published a list of 15 candidate biosignature gases for sub-Neptune exoplanets, molecules with varying degrees of biological specificity, different abiotic escape routes, and different accessibility to current instruments. Among the most striking entries in that list are chlorofluorocarbons, synthetic molecules, chemicals that on Earth are produced only by industrial processes, refrigerants, propellants, manufacturing byproducts. Their detection in an exoplanet atmosphere would not be a biosignature in the biological sense. It would be a technosignature. Evidence not just of life, but of a civilization. A species that had developed industrial chemistry. The same transmission spectroscopy technique, the same instruments, the same analysis pipeline, but an entirely different order of implication. It is worth sitting with that for a moment. The method we are using to search for microbes in a hydrogen ocean could, in principle, find a city. We are not there yet. We are at 3 sigma, contested, with a molecule whose abiotic production cannot be fully excluded and whose biological pathway on this particular world remains entirely theoretical. But the framework being built around this search, the ensemble approach, the expanded candidate list, the methodological lessons from every false positive before this one, is the most rigorous the field has ever produced. Whatever the answer turns out to be at K2-18b, the tools being sharpened on this question will outlast it. Set aside, for a moment, the statistical arguments. Set aside the retrieval models and the calibration disputes and the sigma thresholds. Follow the biological hypothesis wherever it leads and ask an honest question. If something is alive in that ocean, what is its existence actually like? The first and most fundamental constraint is oxygen. There is none. A hydrogen-dominated atmosphere contains no free molecular oxygen, and aerobic respiration, the metabolic engine that powers every animal on Earth, every fungus, every plant, every organism with a nucleus that you have ever encountered, is impossible without it. Any life in K2-18b's ocean belongs entirely to the anaerobic world, to the metabolic strategies that powered all life on this planet for its first 2 billion years, before photosynthetic bacteria began exhaling oxygen and permanently changing the chemistry of the air. That is not a small world. It is an ancient one. The organisms most likely to find K2-18b's environment recognizable are the methanogens, archaea, single-celled organisms that combine hydrogen gas with carbon dioxide and extract energy from the reaction, releasing methane and water as metabolic waste. They do not merely tolerate oxygen-free environments, they require them. They are found in deep-sea mud, in volcanic hot springs, in the digestive systems of animals, anywhere that hydrogen and carbon dioxide are available and oxygen is absent. K2-18b's atmosphere is rich in both. If methanogens, or something metabolically analogous, exist in a Haitian ocean, the atmospheric chemistry above them would be extraordinarily familiar. And the methane they would produce as waste is already present in K2-18b's atmosphere in quantities JWST has measured. That may be coincidence, but methanogens do not produce dimethyl sulfide. The DMS signal, if real and biological, requires something else. Organisms metabolizing sulfur and producing dimethyl sulfide in the process. The Haitian hypothesis does not require K2-18b to harbor one type of organism. It suggests an ecosystem, multiple microbial lineages exploiting different chemical gradients in the same ocean, each producing its own atmospheric exhaust. Methanogens generating the methane, sulfur metabolizing organisms generating the DMS. Their combined output accumulating in the hydrogen sky above, across geological timescales, in an atmosphere that destroys these molecules far more slowly than Earth's would. Now consider the scale problem honestly. Earth's oceans contain an almost incomprehensible quantity of phytoplankton. They produce roughly 100 million tons of dimethyl sulfide every year, the combined output of every ocean on this planet, all of it working continuously. K2-18b's atmospheric DMS concentration is roughly 10,000 times higher than Earth's oceanic levels, even accounting for the slower destruction rate in a hydrogen atmosphere, a factor of perhaps 10 to 100. The biology required to sustain this concentration is enormous. Either the ocean is vastly more productive per cubic meter than any environment on Earth, or the organisms have evolved a DMS production pathway far more efficient than anything in the terrestrial record. Or DMS is not an accidental metabolic byproduct on K2-18b, as it is in Earth's phytoplankton, but a primary product, something actively synthesized at high rates for reasons we cannot yet imagine from this distance. Any of these scenarios describes biology that would be, in its chemistry and its scale, genuinely unlike anything we know. The deep ocean complicates the picture in an important direction. If K2-18b has a geologically active interior, plausible at its mass and age, the ocean floor may be home to hydrothermal vents, cracks in the rock where superheated fluid erupts into cold water above. On Earth, these environments host entire ecosystems that have never required sunlight. Tube worms, eyeless shrimp, dense microbial mats, communities powered entirely by chemical energy released when hot reduced fluid meets cold oxidized water. If such ecosystems exist on K2-18b, they would leave no trace in the atmospheric spectrum. They would simply be there, invisible to the telescope, powered by the planet's interior in permanent darkness. The signal, JWST, is reading, if biological, comes from the upper ocean, close enough to the atmosphere for molecular exhaust to diffuse upward and accumulate. The deep ocean is a separate question entirely, and an unanswerable one with current instruments. Radiation is the final constraint worth taking seriously. K2-18 flares. Its ultraviolet pulses reach the upper layers of the planet's atmosphere periodically, delivering radiation doses to the ocean surface that have no equivalent in Earth's open ocean. Any organisms living near enough to the surface to contribute to the atmospheric signal face this environment directly. On Earth, the answer to radiation stress includes Deinococcus radiodurans, a bacterium capable of surviving doses 10,000 times the lethal threshold for a human being, recovered from nuclear reactor cooling water and Antarctic rocks. Its survival built on an extraordinarily efficient DNA repair system that reconstructs the genome even after hundreds of simultaneous breaks. Its existence does not mean K2-18b has anything like it. It means the niche is physically occupiable. That radiation-tolerant life is not a contradiction in terms. Whatever is in that ocean, if anything is, has had over 2 billion years to adapt to the conditions it faces. 2 billion years of selection pressure, of mutation, of exploration of the chemical space available in a pressurized hydrogen sky ocean orbiting a flaring red star. 2 billion years of organisms that did not survive dying, and organisms that did survive reproducing. By the standards of Earth's own history, that is more than enough time for life to become very, very good at being alive in exactly this environment. The question is whether life ever started. The two scientists most directly responsible for this debate work in the same institution. They probably pass each other in corridors. They may attend the same departmental seminars. They are colleagues in a field small enough that everyone knows everyone, and they have reached opposite conclusions about the most consequential scientific question of the decade. This is not a dysfunction of science. It is science working at full intensity. Niku Madhusudan arrived at this point through a long arc that began in theoretical physics. He moved into astrophysics and then into exoplanet atmospheres, spending years building retrieval models of a sophistication that relatively few groups in the world could match. The 2021 Hycean paper was a statement of ambition, a framework proposing that the most common type of planet in the galaxy had been dismissed as uninhabitable without adequate justification, and that if life existed in the oceans of these worlds, the James Webb Space Telescope would be able to detect its chemical signature. The predictions were noted, questioned, and filed away. Then JWST began collecting data, and the data began matching what Madhusudan had written in mathematics before the telescope had pointed at K2-18b once. When the 2023 NIR spec results came through, his team spent months in what he later described as an active attempt to prove themselves wrong, not to confirm the signal, to destroy it, testing every calibration assumption, modeling every molecule that could plausibly account for the absorption features they were seeing, looking methodically for the explanation that did not require the conclusion they were approaching. The signal persisted. 2 years later, when the MIRI data finished processing and the signal appeared again in a completely separate wavelength window, Madhusudan described it as a shock to the system. He said it takes a while to recover from the enormity of it. Those words were chosen carefully. He is a man trained to qualify, to hedge, to express probability rather than certainty. When the results were published in April of 2025, his team used language that reflected exactly the state of the evidence. Potential biosignature, possible indicators. The language of a scientist who understood precisely what the data could and could not establish, and who was determined that the communication of the result would reflect that precision. The media did not share that determination. Within hours of the preprint appearing, the headlines had translated potential biosignature into life found. Researchers who had not read the full paper were contacted for comment on the discovery of extraterrestrial life. The gap between the careful language of a scientific paper and the declarative language of a news headline is a structural feature of how science reaches the public. Not unique to this case, not belonging to any individual's failure. But it shapes the environment in which the science must now be defended, and it makes skeptical reanalysis look from the outside like an attempt to suppress a discovery rather than what it actually is. The normal functioning of a field that has learned, from hard experience, exactly what happens when extraordinary claims travel faster than the evidence. Oliver Shortall's position in this story is less dramatic, but no less important. He is a geochemist whose instinct is to ask what a planet's interior chemistry would produce before asking what its biology might add. His magma ocean models were not built to attack Madhusudan's work. They were built because the question is scientifically legitimate and had not been properly addressed. When the answer turned out to be a spectrum broadly consistent with what JWST was observing, the same methane, the same carbon dioxide, the same suppressed ammonia, publishing that finding was a straightforward scientific obligation. It is not a counterattack, it is a constraint. A piece of information the field needs to correctly interpret the signal. There is an asymmetry in the debate that neither side disputes. Madhusudan's framework preceded the observation by 4 years. The Hycean paper predicted what JWST would find before JWST looked. Shortall's magma models, whatever their independent scientific merit, were developed primarily in response to data that already existed. A theory that predicts an observation before it is made carries epistemological weight that a theory assembled to explain existing data cannot fully match. This asymmetry does not mean the magma models are wrong. It means the predictive success of the Heysean framework is a genuine piece of evidence in the debate, not merely a rhetorical point. Laura Kreidberg at the Max Planck Institute for Astronomy has said plainly that she has seen this movie before, a reference to the pattern of extraordinary spectral claims and the reanalysis cycles that followed them. Christopher Glein at the Southwest Research Institute put it differently. Unless something is waving at us, it will not be a smoking gun. Both assessments are honest, and both are correct. The signal is not a smoking gun, but neither has it gone away. The argument is unresolved. The scientists on both sides are serious, and the planet continues crossing its star every 33 days, indifferent to the argument being conducted in its name. The argument cannot be resolved by argument. It can only be resolved by data. And the question of where that data will come from, when it will arrive, and what it will be capable of telling us is not abstract. It has specific answers, specific instruments, and a specific timeline that is already in motion. Start with what the James Webb Space Telescope cannot do. JWST was not built for this. The telescope was designed to see the first light of the universe, to peer into the nurseries where stars are born, to study the formation of galaxies in the epoch before our own solar system existed. Exoplanet atmosphere characterization was never in the original brief. It emerged as a consequence of the telescope's mirror size, thermal stability, and instrument sensitivity, a capability the design happened to produce rather than one it was optimized to deliver. At K2-18b's distance of 124 light-years, JWST is operating at or near the edge of what its architecture allows for this kind of measurement. One specific limitation matters more than others right now. Dimethyl sulfide and dimethyl disulfide are structurally related molecules with overlapping spectral absorption features in the wavelength range JWST has examined so far. Distinguishing between them requires observations at longer wavelengths, beyond 12 microns, where their absorption features diverge into separately identifiable patterns. This distinction is not merely academic. Dimethyl disulfide is produced by the decomposition of organic matter, by certain bacterial metabolisms, and by some photochemical reactions involving sulfur compounds. It is a plausible biological molecule, but its production pathways and atmospheric chemistry differ from those of dimethyl sulfide in ways that matter for the interpretation. If the signal at K2-18b comes from dimethyl disulfide rather than dimethyl sulfide, the biological implications narrow somewhat, not because dimethyl disulfide is non-biological, but because its abiotic escape routes are somewhat broader. Knowing which molecule is present would significantly narrow the parameter space of both the biological and the geological models, and it is a measurement JWST has the capacity to make in the right observing configuration. Beyond that, there is the immediate practical bottleneck. Every additional transit observation adds statistical weight. 2 to 3 further observations, combined with the existing data from 2023 and 2025, could push the confidence level from 3 sigma to 5 sigma if the signal is real, or reveal it weakening and dissolving if it is noise. The mathematics is straightforward. The obstacle is not the planet. The obstacle is time. JWST is the most oversubscribed scientific instrument in the history of human science. Thousands of research proposals from astronomers and planetary scientists across dozens of countries compete each year for a finite allocation of observing hours. Every proposal is reviewed by a committee weighing the scientific priority of a given target against every other compelling case in the field simultaneously. The K2-18b transits are individually expensive. Each requires several hours of telescope time during the specific window when the planet is crossing its star, a window that cannot be shifted or extended. And the Cambridge team is not the only group competing for access. Researchers arguing for the magma ocean interpretation. Researchers working on independent analyses of the existing data. and groups studying entirely different planetary systems with equally compelling scientific cases all sit in the same queue. The Cambridge team has submitted proposals for additional K2-18b observations. Whether those proposals are approved and when the resulting data is collected and analysed is the single most important practical constraint standing between the current 3 Sigma hint and a resolved answer. The data may already exist. The analysis may be underway right now in offices in Cambridge and in competing groups around the world. Further out, the next generation of ground-based instruments will transform what is possible. The extremely large telescope is under construction at Cerro Armazones in the Atacama Desert of Chile, at an altitude of over 3,000 meters, where the atmosphere is thin and dry enough to make it among the finest astronomical sights on the surface of the Earth. Its primary mirror is 39 meters across, composed of 798 individually actuated hexagonal segments. Its light-collecting area is roughly 6 times greater than JWST's. The high-resolution spectrographs it will carry are capable of resolving individual molecular absorption lines that JWST's instruments blur into broad, overlapping features, a qualitative step in the ability to read atmospheric chemistry. First light is targeted around 2030. The extremely large telescope is not primarily optimized for K2-18b. At 124 light-years, the planet sits at the far edge of what even this instrument can characterize at the precision required for biosignature searches. Its most powerful capability for this science applies to rocky planets in the nearest red dwarf systems, worlds within 30 to 40 light-years, whose atmospheric features will, for the first time, be resolvable in sufficient detail to search for the oxygen-methane disequilibrium ensemble that K2-18b cannot provide. Planets in the TRAPPIST-1 system, Proxima Centauri b, the handful of potentially habitable rocky worlds close enough to reach with this instrument. Then, decades away, there is the Habitable Worlds Observatory, a proposed NASA mission conceived from the outset for one purpose: the direct imaging of Earth-like planets orbiting Sun-like stars, not transiting sub-Neptunes, true Earth analogues, planets in the habitable zones of stars like our own Sun, their light directly captured by a telescope equipped with a coronagraph that suppresses the overwhelming glare of the parent star, their atmospheric spectra measured in enough detail to search for the full range of biosignature combinations. Planned for launch in the 2040s, it is a machine designed for the next question, not this one. K2-18b will have been resolved long before this telescope opens. K2-18b is the most studied world in the biosignature debate. It is not the only one. The James Webb Space Telescope arrived in science operations with an observation program extending across dozens of exoplanet targets. The K2-18b observations are the most discussed, but they are part of a growing body of atmospheric measurements constituting the first genuine population study of potentially habitable worlds ever attempted. The richest comparative context comes from a system 40 light-years away. TRAPPIST. One is an ultra-cool red dwarf, cooler and smaller even than K2-18, orbited by 7 roughly Earth-sized rocky planets, 3 of them within the habitable zone. It was characterized in detail by Michael Gillen and collaborators in 2017, and immediately became the most intensively studied planetary system beyond our own. JWST has now observed multiple members of the system directly, measuring their thermal emission to constrain surface temperatures and atmospheric properties. The results have been sobering in one direction and illuminating in another. TRAPPIST-1b and TRAPPIST-1c, the innermost planets of the system, appear to have little or no substantial atmosphere. Their dayside temperatures match what bare, airless rock would produce under the stellar flux they receive, not what a meaningful carbon dioxide or nitrogen atmosphere would allow. The atmospheres, if they ever existed, appear to have been stripped by the radiation environment that close-orbiting red dwarf planets face. These are rocky worlds of modest mass, and that mass was insufficient to hold on against sustained stellar bombardment. This is where K2-18b becomes, indirectly, more striking. If rocky planets in the TRAPPIST-1 system have lost their atmospheres, the fact that K218b has retained a massive hydrogen-helium envelope for over 2 billion years says something specific about mass as a protective factor. A world 8.5 times the mass of Earth commands a gravitational field strong enough that even significant atmospheric losses represent a small fraction of the total. Mass protects, and mass here also creates the Hycean possibility. The ocean, the pressure, the extended atmospheric lifespan of the molecules now being debated in the literature. GJ1214b, a sub-Neptune orbiting a red dwarf 40 light-years away, was among the first worlds of this class to receive serious atmospheric characterization. It was studied first by Hubble and then by JWST, and its transmission spectrum is flat and featureless, widely interpreted as high-altitude hazes scattering incoming starlight uniformly across all wavelengths, obscuring whatever molecular features lie beneath. Despite being one of the closest and most studied sub-Neptunes available, GJ1214b has yielded almost nothing about what its atmosphere actually contains. It is a reminder that not every sub-Neptune reveals its chemistry readily, and that the feature-rich spectrum JWST has returned from K218b, however contested its interpretation, represents a genuine scientific opportunity that not every world of this class provides. TOI270d is a more recent addition to the growing population of characterized sub-Neptunes. JWST observations have found a hydrogen-rich atmosphere carrying detectable carbon dioxide and methane, atmospheric features comparable in kind, if not in detail, to what has been found at K218b. It is not a direct analogue. The stellar system is different, the orbital parameters are different, and no DMS detection has been reported. But it demonstrates that the atmospheric chemistry we are trying to understand at K218b is not unique to that one world. It is beginning to appear as a recognizable pattern across the sub-Neptune population that JWST is systematically characterizing for the first time. The sub-Neptune population from JWST is growing. Each new characterization adds a data point to the first population-level study of the most common planetary type in the galaxy, building toward the eventual capacity to ask not whether K218b specifically is alive, but whether the conditions that might support life are common or rare across the entire class. That question requires many data points, many instruments, and years of careful work. K218b is the first, it is not the last. K218b is one planet, one signal, one contested measurement from one instrument pointed at one star in one corner of the Milky Way. And yet the implications of the question it is asking extend far beyond a single detection, far beyond exoplanet science, far beyond astronomy itself. They reach into a problem that has sat at the center of human thinking about the universe for as long as human beings have been capable of framing it. In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues in Los Alamos and asked a question that has never been satisfactorily answered. If the universe is so vast, if there are so many stars, if the conditions for life appear not to be uncommon, if civilizations arise and develop technology, where is everyone? Why does the cosmos appear so silent? Why have we found no signals, no probes, no unambiguous evidence that any other mind has ever looked outward and attempted contact? The question became known as the Fermi paradox, and it is still open. Dozens of proposed solutions exist. The rare Earth hypothesis holds that complex life requires such a specific combination of conditions: planetary mass, stellar type, galactic position, protective gas giant companions, a large stabilizing moon, that technological civilization may be vanishingly rare even in a galaxy of 400 billion stars. The Great Filter hypothesis holds that there is a barrier somewhere on the path from simple chemistry to spacefaring civilization that almost no lineage of life successfully crosses. The silence holds that civilizations destroy themselves before they can make themselves known. No solution is universally accepted. None fully accounts for the completeness of the silence. A confirmed detection of microbial life on K2-18b would transform this calculation immediately and irrevocably. If life arose independently on K2-18b, one of the very first habitable zone planets examined closely by a telescope capable of reading atmospheric chemistry, then life is not a singular miracle. It is not the product of an impossibly specific chain of contingencies occurring once in 400 billion attempts. It is something the universe does. A process, perhaps an inevitable one, wherever liquid water and chemical gradients and stable conditions persist long enough for chemistry to organize itself into self-replication. And if life is common, the Fermi paradox sharpens into something deeply uncomfortable. The Great Filter has two possible locations. It can lie behind us, meaning the hard step, the step that almost never succeeds, was getting from simple chemistry to the first living cell. In that case, confirmed microbial life elsewhere tells us only that we are one of many microbial worlds, and the galaxy may be full of slime and bacteria and nothing more complex. And the silence is merely the silence of organisms that never developed the means or the desire to communicate. That version of the story is strange but not threatening. The alternative is that the filter lies ahead, that the hard step is not the origin of life, but something that happens later, something that intercepts civilizations before they reach the point of making themselves known. Nuclear weapons, climate collapse, the development of technologies that prove impossible to govern at civilizational scale. A species that has had nuclear weapons for 80 years, that has been altering its atmosphere for 30, and that is only beginning to grapple with the implications of artificial intelligence sits in a specific historical moment. If the filter lies ahead, that moment is not abstract. A confirmed detection of microbial life would not answer this question. It would make it impossible to ignore. The history of cosmological discovery is a history of demotions. Copernicus proposed that the Earth orbits the Sun, not the reverse, and the idea was initially treated as heresy. Hubble demonstrated that the fuzzy patches of light called nebulae were in fact entire galaxies, billions of stars apiece, scattered across a universe vastly larger than anyone had imagined, and the implication took decades to fully absorb. Einstein's own equations predicted an expanding universe, and he introduced a mathematical correction, the cosmological constant, specifically to prevent them from implying it. So difficult was the concept to accept. Each discovery moved humanity further from the center. Each was resisted before it was absorbed. Each is now simply the world as it is. Confirmed extraterrestrial life would be the next entry in this sequence and the last one available. The final demotion. The claim that this planet is the only place in the universe where chemistry became biology would be gone, and nothing would replace it. Survey research conducted at the University of Arizona and by colleagues at the SETI Institute has asked people directly what they would feel in response to such a confirmation. The answers are, perhaps surprisingly, not dominated by dread. Most respondents anticipated curiosity, excitement, a sense of awe at the scale of what had been found. The civilizational crisis some commentators predict does not match what people report expecting to experience, but imagining reactions to something unprecedented is inherently unreliable. We have no template. No generation before ours has faced this question with real data, and guessing at our own responses to a situation that has never occurred is an exercise in fiction. Religious and philosophical traditions have been thinking about this possibility more seriously than is sometimes acknowledged. The Vatican's Pontifical Academy of Sciences has addressed the question of extraterrestrial life multiple times, with positions ranging from open inquiry to the view that the existence of life elsewhere would be consistent with theology, an expression of the same creative principle, not a threat to it. Buddhist and Hindu cosmological frameworks have never placed humanity at the center of things in the way that has made the extraterrestrial question feel destabilizing to some Western traditions. They describe a universe of unimaginable scale, populated by countless forms of existence across countless cycles of time. Confirmed life on another world would sit within those frameworks without contradiction. What confirmation would actually look like in practice is worth saying plainly, because the image most of us carry in our heads is wrong. It will not arrive with drama, no ship in the sky, no signal from a distant intelligence, no contact, no communication, no presence anyone can point to and say, there. It will be a graph, a statistical curve crossing a threshold on a computer screen in an office somewhere, a paper uploaded to a preprint server and circulated to the scientific community, a press conference scheduled for 48 hours later, a scientist standing at a podium, choosing words with extraordinary care, saying something that has never been said before. Michael Wong at Carnegie Science looked at the state of this field in the spring of 2025 and said it simply, "What a lucky time to be alive." He was not wrong. So what happens concretely in each direction from here? The first scenario, the additional transit observations are completed, the data is processed, the statistical analysis runs, and the confidence level drops. The curve that was pointing upward flattens or reverses. The dimethyl sulfide feature that appeared in two instruments dissolves when more photons are added to the dataset, or reveals itself under longer wavelength scrutiny to be dimethyl disulfide with a broader set of abiotic explanations, or is ruled out by thermal emission data showing the planet's surface is too hot for liquid water to exist. The signal was real, but not biological. The smell of the sea was chemistry, not life. The ocean was never there. This outcome would not be a failure. Every method developed during the investigation is a permanent contribution. Jake Taylor's unbiased retrieval approach, sharpened against the specific challenges of K2-18b, becomes a standard tool for every future atmospheric analysis. Oliver Shortall's magma atmosphere chemistry framework, the most comprehensive treatment of sub-Neptune interior atmosphere exchange ever published, constrains how the entire class of worlds is understood going forward. Sara Seager's 15-molecule biosignature candidate list, assembled partly in response to the need to go beyond single-molecule detection, will guide the search at every subsequent target. A negative result at K2-18b advances the field by one carefully investigated planet, with better methods and better questions than it had before. The search does not end. Dozens of sub-Neptunes in habitable zones catalogued by Kepler and TESS are waiting for detailed characterization. The full TRAPPIST-1 system remains under active JWST observation. The extremely large telescope will transform what is possible for rocky planets around nearby red dwarfs in the early 2030s. K2-18b was the first close look. If life is out there, the next look is already being planned. The second scenario, the confidence climbs. 4 sigma, then 5. Independent teams at other institutions apply different methods to the same raw data and return the same answer. Methyl chloride is detected alongside dimethyl sulfide, 2 molecules, no shared abiotic pathway, both present simultaneously. The thermal emission data from the secondary eclipse rules out the magma ocean surface temperature. A press conference is scheduled, and the room goes quiet. What is said at that press conference will be chosen with the precision of someone who understands the weight of each word. Not alien life discovered, not life found. Something closer to what the data actually establishes. The detection of multiple co-occurring biosignature gases in the atmosphere of a sub-Neptune in the habitable zone of an M-dwarf, at concentrations inconsistent with known abiotic production pathways, consistent with biological activity in a hydrogen ocean. A sentence that is simultaneously the most important sentence a human being has ever spoken in a scientific context, and a sentence that leaves an enormous amount still to determine. And then the world will try to absorb it. Not instantly, not uniformly. Through argument and reaction and gradual, uneven integration into the stories that human beings tell about who they are and what kind of universe they inhabit. Some people will feel it immediately, as a physical reorientation. Others will need time. Some will find it confirms what they already believed. Some will find it challenges beliefs they did not know they held. None of it will happen the way any prediction about it suggests, because nothing like it has ever happened before. and we are poor judges of how we will respond to the unprecedented. What is true regardless of the outcome? A negative result advances the field and leaves the question open at the next target. A positive result does not merely advance the field, it transforms the context in which every subsequent question is asked. The asymmetry between the two scenarios is not small, it is total. The universe has not made this easy. A signal that is genuine but contested. A world that presents two completely different surfaces to every model that tries to describe it. An answer that is encoded in the chemistry of an atmosphere orbiting a star 124 light-years away, and that can only be unlocked by more photons arriving at a mirror in the dark, more data processed in offices by people arguing in good faith about what the numbers mean. The universe has known the answer for 2 billion years. We have known the question for about a decade. The gap between those two facts is not absence, it is effort. It is the accumulated labor of every instrument built, every method refined, every proposal submitted, every night spent at a keyboard trying to understand what a spectrum is trying to say. What separates us from the answer right now is not ignorance in the deep sense. The physics is understood. The chemistry is understood, within limits. The instruments exist. The planet has been identified. The methods are being refined in real time by researchers who have made this question the work of their lives. What separates us from the answer is patience and rigor, and the willingness to demand 5 sigma before saying the word that cannot be unsaid. Think about the light currently arriving from K2-18. It left that star over a century ago. When those photons began their journey, the first powered aircraft had not yet flown. The first radio transmission had not been broadcast. The confirmation that other galaxies existed beyond the Milky Way was still more than 2 decades away. Albert Einstein was in his mid-20s. The universe was understood to be orders of magnitude smaller and simpler than we now know it to be. Those photons have been traveling through the void ever since, carrying their molecular barcodes, indifferent to what they encode, indifferent to the question that will be asked of them when they finally arrive at the mirror pointed in their direction. And now they are arriving. Now we have an instrument capable of reading what they carry, and what they appear to carry, what 3 sigma of accumulated statistical evidence and 2 independent instruments are suggesting, pending confirmation, is the smell of the sea. Every astronomer who ever turned a telescope on the night sky was centuries away from being able to frame the question we are now asking with data. The astronomers of ancient civilizations who named the constellation Leo, who drew lines between the stars and told stories about what those patterns meant, had no concept of what lay in that direction at any specific distance. No means of knowing that one of those faint lights was a dim red star with a world orbiting it at 13 million miles. The philosophers who argued across 2,000 years for the plurality of worlds, that other suns must have other planets, that the cosmos could not be so vast and so empty, did so without any instrument capable of detecting a single exoplanet. They were right, and they had no way to know it. The scientists who built the first refracting telescopes in the 17th century, who turned them on Jupiter and Saturn and the moons of those worlds, were still centuries away from anything capable of measuring the chemistry of a planetary atmosphere 124 light-years from Earth. We are the first generation for whom that has changed. Not the generation that has the answer. The generation that is close enough to the answer to feel its gravity. That proximity is not nothing. It is, in the span of the whole long arc of human curiosity about this question, almost everything. The signal is there, or it is not. The universe has already decided. The molecules in K2-18b's atmosphere are what they are: dimethyl sulfide from organisms in a hydrogen ocean, or abiotic chemistry from a magma surface, or something we have not yet correctly characterized. And that fact is fixed. It is not waiting for our models to improve before it becomes real. It is already real, 124 light-years away, encoded in the light that has been arriving at this solar system continuously for over a century without anyone able to read it? The answer is not in the future. It is in the present, carried on the same ancient photons that have always been arriving. The future contains only our capacity to read what is already there. What we are doing, right now, in this particular decade of human history, is learning to read it. Slowly, imperfectly, by accumulating photons and arguing about retrieval methods, and submitting telescope proposals and writing papers that other papers disagree with. By building instruments and developing statistics and testing every possible alternative before accepting the most extraordinary conclusion. All of it is the reading. All of it is necessary. None of it is wasted, even when it produces a null result, even when it turns out the signal was noise. The reading is the point. The rigor is what makes an answer rather than a wish. K2-18b transits its star every 33 days. The next observable window is either approaching on a schedule that can be calculated to the day, or the data from it is already sitting in an archive somewhere, waiting for analysis. The planet does not know we are watching. The star does not know we have questions. The transit happens on its 33-day cycle, whether an instrument is pointed at it or not, whether the telescope cue has been approved or rejected, whether the universe turns out to be full of life or silent beyond this single blue world. The specific observations that would resolve the current impasse are known and finite. 2 to 3 additional transits, combined with the existing dataset, push the statistical confidence toward 5 sigma, either solidifying the signal or revealing it as noise. Longer wavelength MIRI observations separate dimethyl sulfide from dimethyl disulfide, identifying which molecule is present and narrowing the biological and geological models. A targeted search for methyl chloride provides an independent biosignature line with no shared abiotic pathway. These are not dreams. They are proposals in a queue. They are data waiting to be collected. And 5 sigma, if it comes, will not be the end of the question. It will be the end of the statistical dispute and the beginning of the next one. 5 sigma means the signal is real beyond reasonable doubt. It does not mean the interpretation is resolved. A confirmed signal at 5 sigma means that something is producing dimethyl sulfide in K2-18b's atmosphere at concentrations 10,000 times higher than anything found in Earth's oceans, and that the question of what that something is becomes the new scientific battleground. Is it a Haitian ocean with sulfur metabolizing organisms exhaling into a hydrogen sky? Is it an abiotic process operating under extreme conditions not yet replicated in any laboratory? Is it something the current models have not anticipated? 5 sigma narrows the argument from whether the signal is real to what the signal means. Both are enormous questions. The second is harder. Right now, in universities and institutes and research groups around the world, there are doctoral students who began their graduate work because of the 2023 announcement. They did not know, when they applied, what the signal would ultimately turn out to be. They applied because the question was the most important question science had ever asked, with real instruments pointed at a real target, and they wanted to be part of answering it. They are writing their first papers now, developing the retrieval methods, the atmospheric models, the statistical frameworks that will characterize not just K2-18b, but the dozens of sub-Neptune worlds that follow it in the observation queue. Some of them will spend their entire careers studying the most common planetary type in the galaxy, a class of world that did not have a confirmed atmospheric detection of any kind a decade ago. Whatever K2-18b turns out to be, this generation of researchers is building the tools that answer the question at the next planet, and the one after that, and the one after that. The question of life beyond Earth is no longer a philosophical exercise. It is a research program. It has funding and instruments and people who have committed their professional lives to it. The next data release, when it comes, will not be slow. A preprint will appear on a public server, and the scientific community will read it overnight. Commentary from independent researchers will begin appearing before morning. Within 24 hours, The statistical headline will be on the front pages of news sites in every language. The question is whether that headline says the signal strengthened, or the signal faded, or the signal resolved into something neither side had fully anticipated. That answer exists right now, encoded in the chemistry of an atmosphere orbiting a dim red star in the direction of Leo, carried toward us at the only speed the universe allows, arriving whether we are ready for it or not. 124 light-years away, the planet turns on its 33-day rhythm, locked to its star, the Terminator wind moving through the hydrogen sky in the same direction it has moved for 2 billion years. Something in that atmosphere is producing a smell you have known your whole life. We do not yet know what it is. We are very close to finding out. The signal is still there.